So this video is about the solution of the picture frame problem, and its relation to the thing called the fundamental group. And so if you haven't watched that video, you should go watch it now. Okay, so let me just remind you real quick what the picture frame problem was. Is that we had a picture frame. We had three nails in the wall, and then we wanted to hang the picture, right, in such a way that first it hangs, and that if I remove any one of the nails, that it'll fall down. Okay, so now I'm going to kind of do the solution in kind of three parts. The first part is I'm going to translate this problem into a problem in group theory. It uses algebraic topology in the fundamental group. The second part of the problem is I'm going to compute the group, right? And then the third part is I'm going to give you the solutions after we compute the groups. Okay, so let's go about so let's start by talking about what fundamental groups are. So fundamental groups associated to this problem. Okay, so all right, so one thing that so let's try and reduce the problem to a couple. So I'm going to just make a kind of series of reductions of this picture frame problem. Okay, so the first thing to observe, right, is that so all paths, all of these. Okay, so I'm going to use the word paths for these wire hanging things. So all of the paths that we'll make, okay, are based at a point P naught in, okay, and so I'm going to use R2. Okay, so here is what we have. So we have our picture, okay, and then we have our point P naught. And then all of these things that they'll go around here, they're directed paths. They do something like this. So all the paths go around like this. Okay, and so they start and end at this fixed point here. Okay. Okay. Another thing is we might as well give these things names, right? So this is what I want to say. So I'm going to do a little picture like this. So we might as well give the x's names. So we should give, so let A, B, and C in R2 be the coordinates of the nails. Okay, and so P0 is also a point in there. Okay, so I might refer to A, B, and C as those points. Okay, okay, so this is the first thing that we can observe. And the second thing is that there's a thing called Homotopia Invariance. Okay, so this problem has I'll do it here. So the paths, you can deform these paths, right? So we can deform paths. This is the, okay, and so I'll draw the picture over here. Okay, and what does that mean? That means that here, right, if I take my paths like this, and I have one that is like, say, like, okay, so if I call this path, so this path is really equivalent to, so if I try to hang the picture frame like this, of course it's going to fall, right? But this thing is equivalent to this thing here. Let's see. I need to go this way. Okay? So if I call this path, say, I don't know, gamma 1, and this path gamma 2, we call these two things are homotopic, right? So in this case, gamma 1 is similar to gamma 2. This relation, that where they can be continuously deformed into each other, this is what we call homotopic paths. Okay, that means that we can deform one into the other. They're allowed to cross, by the way. So like, so this thing is also equivalent to, okay, if I did x, 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 and I did something like here, right? It can cross itself. Okay, that's also allowed. Okay, what is okay? So these things are all homotopic to okay, and then in this example. Above, they are all homotopic to the constant path, are homotopic to the constant path. Okay, so what's the constant path? Okay, and so this thing, the terminology for this is null, null homotopic. Okay, so yeah, so what's the constant path? That is like the string where just like I do nothing. Okay, so there's really, we don't really care about the length of this string in this problem. Okay, so we just kind of just sit there and we don't really move. And all of this path here, since it doesn't go around any of these nails, right? I can reel it in and make it equivalent to nothing. Okay. Okay, so what's an example of non-homotopic paths? So yeah, so let me draw a non-homotopic paths here. So okay, so here's a non-homotopic example. So if I had 3 nails like this, right, and then I had one like this, I took a path like this. If gamma 1 was like this, okay, and then let's say I took the null homotopic path over here. Okay, so we do something like this. Okay, these things are not similar. Okay, why? Well, because in this setup here, right, in order to bring this thing in to deform it, I have to go through that nail, and that's not allowed. We're not allowed to go through that nail. Okay, and so just a quick little bit of notation. So for a path, gamma, let's say, yeah, for path gamma, we let we let this thing gamma denote the equivalence class. So a homotopy is an equivalence relation, right? And we know this denote the equivalence class. Of homotopic paths. Okay, and so one thing that I said is I said that this thing was a group, right? So the group operation, so what's the group operation? So the group operation is concatenation. Okay, so what does concatenation mean? It means that you do one path and then you do another path just shortly following it. Okay, so let's give an example. So let's take a path here like this. Okay, and then I'm going to use the star here to denote concatenation. Okay, and then I'll draw the path here. So this will be the concatenated path. Okay, so let's say we go around here. Okay, let's say we do this one first. Okay, so we'll read it right to left. Okay, so we'll go here. So what we'll first do is we'll go here to here. Let's see. I should have done that the other way. Okay, yeah. Let's write it the other way because I think it'll. Let's see. Let me just think about this drawing real quick. What's gonna happen? Well, okay. Let me just draw it. Right. So we read it right to left. So we first go around this one, and then we go here, and then we go around. Then we go around this one. Here to here. Okay, and so what does this one homotopic do? So we can go here, and then okay. So this one is yeah. I mean, we could write it like this. So this one's homotopic to. Okay, I'll show you why if we do it the other way, it'll look, I mean, it looks a little bit better, but it's not such a big deal. So this one's homotopic to this. We could lift off here, so it looks like a little heart or something. Okay, so this one's homotopic to this path here. Okay, if we did it the other way, right? Okay, so and we always read it right to left like we compose functions. Okay, so let's just do this one real quick. So if we do this path here, and then we do this path, and we concatenate them, so this thing is equal to, okay, so this is, I don't know, we could call this one beta and this one alpha, and this is beta, this one's beta star alpha, and then this is something homotopic to beta star alpha. So this is in the same equivalence class. Okay, so now we look at this one, and let's do this. So we have x here. Okay, so now we go here, around, then we go around like this. Okay, so let's suppose that these were the same thing. So this is alpha, and then this one's beta. Okay, and then this one is alpha star beta. Okay, and this one's homotopic to, say, this path, where I just encapsulate both of those. Oh, sorry, we're going this way. Okay, so these two paths are equivalent. Okay, so now we have an operation. So in order for it to be a group, we need inverses. Okay, so inverses are going backwards. Like the Uno reverse card. Okay, so let's look at this. So let's kind of just draw some inverses. Okay, so we'll go around like this. So let's go, I don't know, let's pick one here. We'll go around this one. Okay, and then we'll concatenate it with, okay, we'll precompose it with the other way around. Okay, so then we go this way. And so this thing is equal to, all right, now I'm going to have to lift this up a little bit. Okay, so this one's equal to, okay, so we start here, and we go around this way first. Okay, and then we go around the other way. Okay, so then we go around this way. Okay, and so what's this thing equivalent to? So this allows us to kind of lift it off, where you can go like this. Okay, so it goes around, we run around this way, and then we came back the other way. Okay, so, and then this is null homotopic. This one here is null homotopic. That's a null homotopic path. So if we take this path and then we do its reverse, well, we see we get something like this, and then only the endpoints are pinned. So we can lift up that middle point and move it around and get something that's homotopic to the identity of our group. The identity of our group is the constant path. All right. So now we have a group. All right. So this group, okay, so the group that we have, so I promised a group. So the fundamental group, right? So this is equal to the homotopy classes of paths, homotopy classes of paths, closed paths, based at P naught under concatenation. Concat. Okay, so this is a group. In our particular case, this is the notation for this. Okay, since they're so this is pi 1. We take our space that we're looking at here, and we removed 3 points, A, B, and C, and then we looked at based at the point P naught. And so this is the fundamental group of R2 minus 3 points based at P naught. And that's the definition of the group. Okay, so now we can talk about translating the problem. Now we've kind of described what the fundamental group is. I have this tool, and now I'm going to use the tool to talk about, to reformulate this problem. Okay, so the problem was, right, how do I hang the picture, right, so that first it hangs, right, and that if I remove any one of these points, that it'll be 0. Okay, so so there's two things: is that the fact that the picture frame hangs. Okay, so there's so the translation of the problem. Okay, so the picture frame hanging. Okay, the picture frame hangs. Okay, so this means this is equivalent to, so we'll say that this is the same thing as, it doesn't really need to be, we don't really care about the orientation. It's a math problem, so I just care that it'll stay. So the picture frame hangs is, so this is equivalent to the element of the fundamental group. So find W in pi 1 of R2 A, B, C, P. Okay, we could have called this thing just G if we wanted to. Non-zero. Okay, and then the removing the nail bit. Okay, so removing the nail. Okay, so it means that the path, okay, so this thing here means that the path becomes, so the path becomes null homotopic in R2. Okay, so we can just write all these R2AB, R2AC, and R2 set minus BC. So if I just plug in any of the 2 points, right? So if I were to take this thing instead of looking at it minus 3 points, if I did it minus 2 points, we want this path to become, homotopic to the constant path, the stupid path. Okay, and in particular, what this means is that we have more precisely. Okay, so there are 3 group homomorphisms, right? So we have 3 group homomorphisms. So we have R2 A, B, C. Okay, and then we have, I'm omitting the base point. Okay, I'm just going to omit the base point in this notation. I'm tired of writing it. Okay, so we have 3 other alternatives, AC, and then we have R2 BC. That's not supposed to be there. Okay, so we have pi 1 of this, we have pi 1 of this, we have pi 1 of this. Okay, and then we have 3 group homomorphisms. Let's call this one H. Let's call this one H, G, and F. Okay, and so we want the condition that we have is that, so this condition here is that F, so is that F of W, whatever the word is, so whatever this thing is, sorry, I called it a word, I'm giving away something about what this group looks like. It turns out to be the free group on 3 generators, okay? But so the condition is that we want this thing to be 1, we want this thing to be the identity, So we want it to be in the kernel, so the kernel of all three maps. Okay, so this is the condition that we have. So, okay, so now we have our fundamental group, now, and we now have the translation of the problem. The picture hanging means that this element of the fundamental group is non-zero, and the fact that after removing a nail, it falls down is the same thing as saying that that it's either going to be, the path is going to be null homotopic if I consider it in one of these fundamental groups, or equivalently, that the image under these three group homomorphisms is going to be 0. And the group homomorphism is you take a path here, and then you consider its equivalence class in these groups. Okay? So any path here is a path here, because this thing has even fewer points. So we don't have to worry about, if it doesn't pass through C, if it doesn't pass through A, B, and C, it doesn't pass through A and B, and we're still okay. Okay, again, these are all based at P naught, but I just remove that notation for simplicity. Okay, so we have the translation of the problem. So we have this fundamental group. We have the translation of the problem, and now what do we have? So now I need to tell you about we need to figure out what these groups are. Okay, so this is kind of the computation of the fundamental group. All right. So okay, so in math, whenever you have a hard problem that's too hard, what do? You go to an easier problem. So instead of just describing the fundamental group of the plane, the Euclidean plane minus 3 points, let's just do the fundamental group of okay, so here's the fundamental group of the plane minus 1 point. Okay, so the easier problem is pi 1 of R2 set minus a single point A. This is based at P naught. So this is equal to what? Okay, so this is the easier problem that we should handle. Okay, so all right. So here is the idea, right? So we kind of have just two things. So here's our plane. Here's P naught. Okay, so this is A, right? The point that we removed. So we have things that are null homotopic. Okay, so these things are equivalent to this is equivalent to the constant. Okay, I'll just write it like that. Right. So this is this is the constant loop. Okay, this doesn't do anything. We also have elements that are not null homotopic, right? Like this. Okay, the ones that go counterclockwise here, like this. So this is not null homotopic. Okay. So, all right. So it turns out that this is really the only thing that matters, right? So the only thing that matters is how many times it winds around this point, right? So and I'm not going to prove that rigorously, but the only thing that matters, right, is how many times it winds. So let's call this thing alpha. Okay, it winds around A. Around A. Okay, so this is alpha. Okay, so alpha inverse would be the reverse path. Okay, and so if we had a path like, okay, and so the claim that I have is, the claim here is that this thing here, a P naught. So this is generated. This is equal to the free group generated by. Okay, so let's. So we need to give this a name or something. So okay. So I don't want to write this every time because it's going to be annoying. Okay, this is true. It's the homotopy class of alpha, right? So this is just this thing here is okay. So this is this is true. This is true. All right, I'm going to write that as a claim. But let me just kind of okay. So I'm going to do some abuse. Okay, I'm going to just omit the brackets and write this for the homotopy class. Okay, so and I'm just going to omit that. So I'm just going to work with these things. Okay, so sorry. Okay, it just looks so ugly to do it like this all the time. Okay, so what is this thing though? Okay, so here I'm writing this abusively. Okay, and this thing is just so this thing is the set of alpha to the n for n an integer. Okay, so this is so it's equal to dot 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 alpha to the -1, the identity alpha squared dot 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 like this. So these are all the elements, and then if you alpha to the a, let's say alpha to the n times alpha to the m. This is alpha to the n plus m. Okay, so this group is actually isomorphic to the integers, right? So the integers under addition. So this is the free group on one element. This is a free group on one element. Let me get a new pen. Actually, I'm not going to. Okay, so this is the free group on one element. Excuse me. Okay, so okay, let me just kind of just to clarify things, right? So alpha. So if I raise alpha to a power, it just means alpha concatenated with alpha. Okay, so I'm using the multiplication operation of star, and I'm just not writing it down every time. Okay, so like for example, right? If I took this path here, if I did this thing, so I went around this loop, and then I went around this loop again. So this is, say, gamma 1 star gamma 2, right? So this thing is equivalent to, well, if I just, it's hard to write it like this. So this thing is well, okay, I'm just gonna do it like that. Okay, so this is really alpha squared. It goes around twice. Oh, this pen's not very good at it either. Okay, so let me get a better pen. Oh, do I have pens? Oh, there we go. Okay. I gotta remember why I stopped using these Sharpies. Okay, so what am I doing now? I am, so this is what we were talking about. So we computed the fundamental group of pi 1 of z. By the way, okay, so by the by, oh, that's nice. Okay, so let's look at, so R2, so if we take R2 minus a point, okay, so let's just look at this. So that's the point A. So here's the, okay, so I need to draw a bunch of spaces. So this is R2 minus a point. You can't really see it. This is the whole picture. Okay, so like maybe it's in this frame. Okay, so this picture is the same thing as, okay, if I shrank everything out like this, okay, and so I did it like this, and then, so here's the negative space here. So this is like, so now this is just a ball, right, minus a point, okay? And that thing is equivalent to, well, if I can fatten this up, okay, so now I'm looking at all the things that I can deform. Okay, so now I have this ball, and then I have this ball. Oh, I'm going to get such a headache from this one. Okay, so so I have this ball. Okay, sorry. So now I removed the disc. I've kind of fattened this thing up. Okay, and this thing is just, okay, what's all left over is this very thin piece here. Just this very thin white thing. Okay. Okay, and then if I invert colors, right, this is just the circle, right? And sometimes we call the circle S1. Okay, so this is the circle. So if I really puncture this, right, if I puncture this, it's deformation equivalent to this thing to the circle. So that sometimes we say that these two things have the same homotopy type. And in this one, it's really easy to see that, here, let me just write down that statement here. A, so this is, this is S1. So this is the same, so this means that they have the same homotopy type. The same homotopy type. And maybe in this one, it's a little bit easier to visualize what the fundamental group of, and so let's say the P naught is down here still, okay? So, so now, maybe it's easier to visualize that S1 P naught, so that this thing here is a cyclic group of, so this thing is a cyclic group generated by one element. Okay, so here, for the circle, you really only have, so if you're going to take a path, you can only go around the circle, and you're either going to go around a couple times, or you're going to go here and back, and then in that case, you can just reel it in. So it just measures the winding around a single point, okay? So the fundamental group, so the lingo for that is that the fundamental group only depends on the homotopy type of the space. Okay, so all right, so we did one puncture, right? Let's do a slightly harder problem, right? So let's do the next case. All right, so next case, all right, is R2 minus 2 points. Okay, and so in this case, right, we can do the same sort of deformation trick and to figure out what the fundamental group is. And so here, so let's look at 2 points here. Okay, so this thing is equivalent to, well, I'll bring in the outside again, like we did before. So I bring all the outside space in. So this is like the same thing as I take another way to think about that is that I take any loops that I have, and I'm just going to bring them in so that I'm going to deform them so that they're all within a certain disk. Okay, so I kind of reel them in and bring them in so that they're within a certain size. And again, we can now remove the two disks like this. So this thing's equivalent to something like this. So we just have like a disk with two disks removed in it. Okay, and now this thing here, so this is equivalent to, well, okay, so now it's kind of like an infinity sign, right? If I were going to, okay, I'm going to try and do it like this. All right. Okay, and then I'm going to invert colors now. right? And when we invert colors, what do we get? We get this thing and this thing. So it's like a circle and another circle, okay? And this has a name. This is called, the fancy name for this is the wedge product of two circles. So it's two circles with the 2 points identified. Okay, then this is the operation that you have. So it means glue along a common point. And we could say that this common point is maybe P naught. Okay, and so what does the fundamental group of this thing look like? So pi 1 of S1 wedge S1. So again, it turns out that all of these paths here, right, they can be deformed into paths that just go around these two things. Okay, so pi 1 of R2 set minus AB based at P naught. So this is the same thing as pi 1 of, you know, these two circles, right, based at P naught. And then this thing here is really generated by two classes, right? So here, right, you only have really two options for your paths. You can go around this loop, right, or you can go around this loop, right? And then here, this is the free group on two generators. Okay, so so this is all the words that you can make out of alpha and beta. So what does this thing look like? So so let's. Okay, so what does this thing look like? So so alpha beta here. So this is the free group on two generators, and so it contains elements like alpha beta, alpha inverse, beta squared, alpha, and alpha inverse beta. Let's do it like this. So this one here, you're actually allowed to contract those, right, because they're next to each other, but you can't commute the b's and the alphas. So this is 1 times beta alpha, and then this is just beta alpha. Okay, so this thing is in here. Okay, so this is, you just make all the words that you can out of this, but the two letters are not allowed to commute. So the two letters do not commute. Letters do not commute. Okay, so all right. So yeah, so we kind of have like two things, and maybe like another way to think about this is that we have A and we have B here, and we have our point here P, and that this is the homotopy class around this one, and this is the homotopy, so alpha and beta. So this is the homotopy class. So I'm not necessarily saying that this picture here corresponds to this picture here under the deformation. I'm just giving these another name, and it'll be isomorphic, right? It'll be generated by these two things. But you have this loop here and this loop here, and up to homotopy, those are the only two loops, and then it's the free group generated on those. That is the this is the generators. These are generators for the fundamental group of pi 1 R2 set minus AB based at P naught. Okay, so another thing that's easy about this to see is okay. So what does so we have so we're talking about these group homomorphisms, right? So what about this? This is maybe the easiest one to possibly do. If I go like this, okay, so what is this map here? If I just take A, okay, so this thing is just generated by alpha. This thing's generated by alpha beta, okay? And we could take our example words. So what is this group homomorphism? I don't know. What do we want to call this thing? F or something, okay? So this is our map here, F. And if I take alpha beta, alpha inverse beta squared alpha, and I take f of this. So what is f of this? So all it does is it replaces all the betas with 1s. So this is alpha 1, alpha inverse 1 squared alpha. And so this is just alpha. Okay, and if I were to take the other one, so I did beta alpha, this is also alpha. So alpha times 1. Okay, so this is what the group homomorphism looks like. It just, all that you do is like this. And maybe we can look at what this does. So if I do alpha, okay, so let's, so what is it doing geometrically, right? So if I did, so let's do, okay. So what are we removing? We're removing, we plug in beta here. Okay, so we did A, B, okay? And then let's take a loop like this. Okay, so if we did a loop like this, so this thing is really beta then alpha. So this is beta times alpha, this one, this thing here. And so if we did this, so now we like fill it in, right? Fill, right? And we do this. Okay, so this thing, this thing now becomes equivalent to just alpha, right? Oh, like this. So this is under the map F. Okay, under the map F, right, where we fill this in, this thing gets filled in, and then this beta becomes a kernel, an element of the kernel of that group homomorphism. All right, so now you can kind of guess what's going to happen. So now in the general case, so in the case, our case, right, so we have R3 set minus 3 points, A, B, and C. Well, it turns out that this thing here is deformation equivalent to the wedge of 3 spheres, right? And it turns out that we can compute this thing. So pi 1 of R3 set minus A, B, C. So what does the wedge of 3 spheres look like, by the way? So let's draw that. Okay, so that's 3 spheres. They meet at P naught. Okay, so this thing here is the free group. So this is a free group on 3 generators. Okay, so it's just all these words that we have here. Okay, and now so this is our problem. Okay, and so now we can talk about the solution of our problem. Okay, so what's the solution? Okay, so we have 3 groups. Okay, so now we have a problem in pure algebra, right? So we have alpha, beta, gamma. That's the fundamental group. That's our fundamental group. And then we have the 3 punctures, alpha, beta, alpha, gamma, beta, gamma. Okay, and we can give these, we gave these names. So this was H, G, and F. So these are 3 group homomorphisms. Right, the 3 amigos, 3 group homomorphisms. Okay, and what were we looking for? So we were looking for a word in here, right, such that that it goes to 0 or goes to the identity. It's a non-trivial word that goes to the identity on all of these things. So let's look at a non-trivial word. Okay, so we want a non-trivial word. All right, so we want a word. So we need W in this group, gamma, such that W is not the identity, and H of W is equal to 1, G of W is equal to 1, and F of W is equal to 1. So 1 is the notation that we're giving for the constant path, okay? Or the identity of this group, the empty string, if you will. Okay, so this is what we need. All right, so So let's look at an example of what could happen. So if we take W to be this word, let's just write something down, alpha, beta, gamma, alpha inverse, gamma inverse. Okay? So so what is this? What happens, just for clarity? So H of W is, what's H of W, what's G of W, and what's F of W? Okay, so H of W, well, that thing sends gamma to 1. So this is alpha, beta, alpha inverse. What's G of W? So that sends beta to 1. So this is alpha, gamma, alpha inverse, gamma inverse. And what's F of W? So that sends alpha to 1. So that is beta, gamma, gamma inverse, which is just beta. All right. So this is how we compute with this thing. Okay. So here's so this is the section that's on the solution. And so to answer the problem, I need to introduce some notation. Okay. So there's a thing called the commutator. Okay. So for a group, we're going to write this x, y, x inverse, y inverse. Okay, so if these two elements commuted in a group, it would be 0. And so like if these are generators of a free group, they're not going to commute. Okay, and so our word, so the solution that you can check on your own is the following. Okay, so what we'll do is we'll do alpha, beta. Okay, so, and we're going to do gamma. Then we're going to do alpha, beta inverse. Okay, and then we're going to do, maybe we'll write this out, gamma inverse. Okay, so this is going to be our word W. Okay, so let's kind of check what this does. Okay, I'm just doing this so that we're all familiar with group notation. So, okay, so notice that if gamma goes to 1, right, then this thing, if gamma goes to 1, then what are you left? You're left with this times this, and that's 0. If alpha goes to 1, okay, if alpha goes to 1, well, that'd be like x going to 1 in here. If x goes to 1 in here, then you have y times y inverse, and that's 1. And then these two gammas, so then this thing just becomes 1, and this thing becomes 1. And then these two things become next to each other, and they cancel. Okay? Same thing if x, so what did I say, alpha? So if alpha goes to 1 or beta goes to 1, the same thing happens, right? The commutators are going to vanish, and then you're left with these two things on their own, and it'll go to 1. Okay? And then this is a non-trivial element. Okay, so just to make sure that we all know how the group operations work, I'm just going to write this element down, but maybe you can leave the video if you want. But so let me just say here. So we have this. So we're going to write down this element: alpha, beta, alpha inverse, beta inverse, inverse. Okay, gamma, alpha, beta, alpha inverse, beta inverse. Okay, so so the only reason I really wanted to do this was to show you what this thing actually worked like. So just in case. For the people in commutative algebra, how do you do this? So to take an inverse, right, you flip everything and you invert. So the rule for inverses is that xy inverse is y inverse x inverse. And that's because if you do xy times y inverse x inverse, right, well, these cancel, right? Well, those cancel, right? And then you're stuck with these. These cancel, and this is 1. Okay? So that's how this works. And then we have this uniqueness of inverses. So whenever you have an inverse and you show that something is the inverse, then it must be the unique inverse. Okay, so let's figure out what this is. So then this is beta. So what I did is I'm taking each element, and then I'm putting this one over, and then I'm putting its inverse. So now I have alpha, and then I have beta inverse, alpha inverse. Okay? So, and then this is gamma, alpha, beta, alpha inverse, beta inverse. All right, that's all I have to say about that. Okay?